Hello and welcome to Toddcast number 9. This is actually going to be first of two parts on resonance. So 9 and 10, I'm anticipating will both cover the topic of resonance, which just based on that alone should make you realize this is one of the major topics coming out of organic chemistry. So to this point, everything has been review, or if it's not review, it's things you've seen before, maybe weren't explained, like line bond drawings, things you probably have picked up over time. This I anticipate is the first of the new material. You touch it a little bit in GChem, but at the level of OChem, or what we're going to be doing, much deeper. So I want to just start with the word resonance. You're actually going to see this in many different areas. In music, they talk about it. In physics, they talk about it. In OChem, they talk about it. And we apply the word slightly differently in each case, but resonating still comes down to, in essence, vibrating or oscillating, going between multiple forms. We're going to consider usually two, possibly three different resonance structures. So a way a molecule can exist might exist one way for a small amount of time and the other way for a small amount of time, and it just oscillates back and forth between that. And the more ways you can exist, the more ways you can spread out your electron density in a stable fashion, the more stable the molecule. So resonance is a stabilizing feature of molecules. I'm going to start with the basic idea that what it is sharing electron density through what we call delocalized orbitals. So it's basically a p orbital. So for sigma bonds, those electrons are always fixed between the nuclei. So if you have two atoms making a bond, let's say a carbon-carbon bond, the sigma electrons will be predominantly between the two nuclei. Occasionally, they might be outside the nuclei, but they are said to be localized. So you cannot share sigma bond electrons from one sigma bond to another to another. They're localized. Whereas pi bonds are free to move around because they're not bound by that strong internuclear force. They can go from one atom to another to another. So resonance is a phenomenon associated with p orbitals, which means it can only occur when you have at least one pi bond or the ability to make one pi bond. And in general, it's going to be an extended network of pi bonds or p orbitals. So in the simplest thought, I want to start with these three neighboring p orbitals. So there's an undefined carbon here, or unspecified, but we assume it to be true, carbon nucleus. So I'm going to just say those are three carbon atoms. It doesn't necessarily have to be carbon. It could easily be carbon, nitrogen, and oxygen. Anything with a p orbital will work. But let's consider for a moment some electrons in this. So let's say we had one electron in this, one electron in this one, two electrons in this. So we have, in essence, a bond here, and then a lone pair on a neighboring atom. So it should look something like this. So if we were to draw the line bond representation, you have a carbon with a double bond to a central carbon with a double part of a double bond connected to this third carbon, which carries a lone pair. So because these electrons are not localized, centrally located on this bond, they're free to move. So this one in theory could move here, this one could move here, they can move all around. But there's got to be a rhyme and reason to the way they move. Every carbon wants to retain its electron if it only has one, but the one with two is free to share. So there is a chance this electron can bump over here, which could bump this electron over here. So in other words, follow what happens to these electrons. If you need to replay it. But right now I have 1, 1, and 2. If they move in the following fashion, now I have 2, 1, and 1. So this electron used to be here, this electron used to be there. How I draw that in a line bond representation is I would show that this electron went and became part of the pi bond because my pi bond is now here. And these electrons in this pi bond are now localized. So we draw it by a curved arrow. So a two-headed arrow means we're considering both electrons to move, even though in the end there's one. Pictorially, I'm going to represent it as both move over. So they're now shared between this group, and this one that used to be a pi bond is now a lone pair. When you have resonance structures, you get a double-headed arrow, implying that it's not an equilibrium, it's a movement of electrons. Equilibrium implies some sort of reaction or some sort of movement of a nucleus. No nucleus moves, so we're going to say this is just single-headed arrows on each side, it's resonance. So what I have here is now represented by 2 electrons on the left terminal carbon and a pi bond now existing between the middle and the right carbon. So this is the way we're going to see it over and over, this line bond drawing, but really it represents this. And like I said, resonance implies going back and forth. So I only showed going this way. You can do the same thing. These electrons, this one can move back to the middle, this one can move back over here. So it could do this arrangement right there. We'd represent that now as a lone pair going in to form a pi bond and a pi bond coming out to form a lone pair. So if you see this in the most basic fashion, everything has to be in p orbitals. So that means we can only deal with pi bonds and lone pairs. And real simply put, you're going to get either a lone pair becoming a pi bond becoming a lone pair, or both every single time. So just if you focus on that, it's just a p orbital phenomenon, and you have 2 options. A lone pair becomes a pi bond, or a pi bond becomes a lone pair, or in this case, both. You have to look for that. So let me just, as drawn here, let's look at this. This lone pair is turning into a pi bond, check. And this pi bond is turning into a lone pair when it goes back to this structure. When we went the other way, a lone pair went in, pi bond broke. So a lone pair became a pi bond became a lone pair. It may seem like it's why am I doing this? It's oversimplistic at first. It's I know it's more complicated down the road, and it'll get more complicated when we start adding more atoms into the chain. But it really is as simple as pi bonds become lone pairs become pi bonds. And because of this stability, because you can now share electron density across 3 atoms instead of just 2, it adds more stability. It's that whole concept of diversifying. So if you spread everything you have into a larger pool of locations, there's less chance of having something stolen or losing something. It's just, you spread it out. Not the best analogy, and I'm kind of regretting doing it, but I'll still go with it. You're sharing electron density across. The more you share it, the more stable it's going to be. So I want to talk about this concept. I mentioned delocalization. I want to figure out what that means. Localization, like we talked about with sigma, and delocalized with pi. And it's the word we use in chemistry, so I'm going to stick with it. But localized means limited, imprisoned, held captive. These are pretty strong words, but they work. Whatever charge you have, whatever electrons you have, whatever you're interested in, it cannot move anywhere else. It is isolated on one location. It is local to just that one carbon. Delocalization is the ability for that charge to move around, those electrons move around. You can share amongst multiple atoms. So it's a concept that honestly I didn't get perfectly when I first learned it, because I didn't really take time to think that the word they're using isn't exactly what they're trying to describe. And so it's important, if it helps for you, to change it to just say shareable and then imprisoned. So maybe those are strong words, but it works. This electron pair here, lone pair becomes a pi bond becomes a lone pair. So in the beginning, we have a lone pair on this terminal carbon, comes in, becomes a pi bond, check. This pi bond moves over, becomes a lone pair, right there, check. Negative charge, if this extra pair of electrons causes a negative, then the negative has moved over. Notice it went every other. It went from end, skipped the middle, and went to that carbon. So when negative charge moves around through resonance, when you have a lone pair becoming pi bond and pi bond becoming lone pair both, you go every other. You're going to see this every other pretty often. Again, a 2-headed arrow to describe the fact it's resonance, meaning no nuclei moved, only electrons through the pi network. Here we have a different type of resonance. So you have a lone pair on this. I'm going to redraw this a little bit. Hopefully it's a little bit cleaner. But you have a lone pair on that oxygen. You actually have 2, one of which is now going to form a pi bond. So lone pair becomes a pi bond. This is that case where only one of the 2 things is happening. So earlier I said lone pair becomes a pi bond, or pi bond becomes a lone pair. That's an or case. This is a up top an and case. Lone pair becomes a pi bond becomes a lone pair. Here, lone pair becomes a pi bond. Those electrons move over from localized or on the oxygen to now being shared. They can be shared between the oxygen and the carbon. Notice you have a charge in the beginning, you have a charge in the end. If electrons move towards you, you added negative, cancels out the positive charge. If you lose electrons, if they move away, if you lose a negative, you become a positive. It had two lone pairs, it now has one. It had no pi bond, it now has one. So this is a delocalized system. So delocalized electrons can only do it through a p orbital system. So sharing in a pi network or 3p orbitals, sharing in a pi bond, 2p orbitals. Over here, this lone pair is stuck in an sp3 hybridized orbital connected to just sigma bonds. It cannot be shared. It is imprisoned, it is held captive, it can only be on that first carbon. The nicer way of saying it, it is localized to that carbon. This plus charge, we can't move electrons over without also taking a nucleus. So we say that is localized. That plus charge cannot move to another carbon without breaking actual bonds, moving actual nuclei. Okay, so I think that's a decent start. I want to draw a picture of this here. And so I've used a pre-drawn picture, but I want to figure out how this picture came into being. So we have a 5-carbon species. I'm going to try to draw it planar. So I'm going to draw the bonds as such with the O here. And emphasizing that this O has two lone pairs. One lone pair, I can make a p orbital. Another one, I can make an sp2. That's sp2. That's in a p orbital. On the neighboring carbon, and I drew it disproportionately long because I want to emphasize this is the bond we're interested in. So I'm matching this picture right here. This is where we started with our plus charge on this carbon right here. So I'm going to draw that as carbon instead of a dot. These electrons, just like before, are free to move over. So I can take one of these electrons here and then move it over to here and form a bond. So all we've done is we've taken these electrons and let them move over. So this line right there represents the sharing and forming of a pi bond. Hopefully this makes sense. That wedge coming out, that dash going back in, shows three-dimensional accuracy. I don't know whether the prefab drawing or my drawing helps more, or hopefully it in some way, but I'm going to erase my drawing and stick with the one that's drawn there. And say the lone pair is in a 2p or p orbital, so it can overlap or share. So the key thing, in order to have delocalized electrons, you have to be in a p orbital. So these both have to be p orbitals to share. sp2 cannot. So a really good example of that is a molecule known as pyridine. So pyridine, if I draw this sideways, I'm going to draw my nitrogen here. I'm going to draw these bonds as such. This pi bond right here, I'm going to say from nitrogen, I'll say this is the first carbon. So this pi bond I'm going to do in red. That pi bond is there. I'll do this pi bond here in yellow. I'll do it better. There. And I'll do this one in green. And then it can resonate like this. So you can have orbital overlap across the different orbitals. So this is, hopefully it's somewhat clear the way it's coming in. But the key thing I'm interested in is this lone pair right here. It has to be in an sp2 hybrid. sp2s go on to form sigma bonds. Sigma bonds cannot be delocalized. So this lone pair right here is trapped in an sp sigma oriented hybrid orbital. Can't be shared. Only the p electrons, only the pi bonds made from p orbitals can be shared. Okay, so hopefully this is seeming clear. So I'm going to erase my picture. Sorry, I do it this way. I just want to leave some of my first drawings there. And just point out, the lone pair is an sp2 hybrid orbital. So it is imprisoned. It's held captive. It can't move. So there is no resonance for this one. This becomes somewhat important when you get into biochem and you deal with an amino acid known as histidine. And so we'll use that as an example later on this chapter. But for now, just go into the rules. So we've seen what delocalization is, a sharing of electrons. That's the foundation of resonance. Few rules to follow. Number one, the nuclei, as I mentioned, do not move. Only pi electrons move. So the actual center of each atom can vibrate, but it will not move from one position to another position on the molecule. Only electrons move, and specifically, only pi electrons move, not sigma. All contributing structures must have the same net charge. So you notice how we had a plus charge on an O that turned into plus charge on carbon, or a negative charge on a carbon that turns into negative charge on N if we drew something like that. But your total number of electrons and your total number of charges, your net charge, has to stay the same. Not total number of charge sites, but your net charge. So if you had a -1, you could have a resonance structure that had a minus, and a plus, as long as it adds up to overall -1. And the electrons you can't make or break, can't lose, can't gain. You can only move electrons. So the total number of electrons has to stay constant. Second period elements, nitrogen, oxygen, carbon, the ones we're going to use most often, cannot exceed an octet, but they can have less. You can have what's going to be known as a carbocation, a carbon that only has 3 bonds, and it is missing electrons. So it'll have, in essence, an empty p orbital. Hydrogen atoms can only form a single bond, that I think we're good with. The third period elements can have up to 12 valence electrons. So sulfur, some of the halogens, they're going to mess things up a little bit. Phosphorus can have up to 10 bonds. So when we involve them in resonance, it's a little trickier, but it's still the same set of rules. Pi bonds become lone pairs become pi bonds. Always include lone pairs when they're there, because they're part of the resonance system. And informal charges, always make sure you keep track of where they're located, which atoms they're on. Okay, you can go back and memorize those rules, but honestly, they're just learned through practice. But as you're going through your first few examples, have a list of rules by your side and make sure you're following the rules. But I still think the bigger thing to do is always identify, have I made a lone pair a pi bond? Have I made a pi bond a lone pair? Have I done it twice? Have I done it 3 times? Is it just one of those? Identify how you're doing it. So again, lone pair is going to become a pi bond is going to become a lone pair. Oftentimes it's both. So that same example we had before, this lone pair turns into a pi bond, this pi bond turns into a lone pair. So I need to draw a double-headed arrow and then the end result. So this electron movement generates a lone pair. This electron movement turns a lone pair into a pi bond. Okay, some of the other types we'll have. So this is one we've looked at. We can also start with a pi bond and turn it into just a charge. So we saw the opposite of that before, but look at this one. So instead of, not the opposite, but a different case of that. So we looked at 2 atoms. Here is 3 atoms. So if you have a plus charge here, it is lacking electrons. The electrons go from where they are to where they aren't. So there are electrons in this pi bond, but this is an empty p orbital. So these electrons can move over and form a pi bond, meaning this pi bond moves over and becomes a pi bond somewhere else. Okay, breaks my rule about pi bonds become lone pairs become pi bonds. This just became a pi bond at a different location. So the way we typically draw that is we have the 3 carbons of interest here, here, and here. And notice how the N carbon and the N carbon can carry positive charges. Well, reality is because it's resonating, because it's bouncing back and forth between these two structures, half the time it'll be positive on the right, half the time positive on the left. So we put a delta plus and a delta plus that if you really wanted to be specific, plus 1/2 and plus 1/2. Okay. You can also have an allylic negative charge turn into a pi bond. So allylic means it is adjacent to a pi bond. So if you have a pi bond here and you go down the alley, you'll end up with a lone pair. So we call it allylic is a description of a carbon that is one away from a pi bond. Okay, so notice this looks identical to what we did up here. Lone pair becomes a pi bond becomes a lone pair. So why am I listing 1 and 3 as different cases? Really, it's as simple as in one case, it's neutral moving over. The other case, it's negative. And so I probably need to pay better attention to charges because reality, if I move this over, I probably left behind a positive. I probably created a negative. So this is generic. This can definitely happen. But reality is we should keep track of charges. So this is a general example of motion. This is a more specific example of how we'll see it in some of the real examples. So notice the exact same thing, but the negative charge moved every other. Went from far left, past the middle, and ended up on the far right. Just like up here, charge was on the far right and ended up on the far left. So this one, just like we drew the hybrid here, dashed lines represent sometimes here, sometimes there. We do the same thing. We're going to draw the same structure. Dashed lines, meaning sometimes a pi bond is here, sometimes a pi bond is here, sometimes negative here, sometimes negative there. So just like we said, delta plus or plus 1/2 at each end, here we have minus 1/2 at each end. Half the time it's here, half the time it's here. And then lone pair is going to go to an adjacent plus charge. So we did do this one with that O donating in. But when we do it, when we lose electrons, we're going to gain a plus charge. When we gain electrons, we negate the plus charge. So this first one, generic, 2, 3, and 4, more specific cases of how we pay attention to the charge movement. So this is a case where our hybrid would simply have plus delta plus here and delta plus here. Notice I tossed in a very specific example involving nitrogen, because that's really common case. Same with oxygen. So if I had a case where I had a lone pair on nitrogen and a positive on the carbon, electrons could come from nitrogen and donate in, and then I put the plus on nitrogen and the negative on carbon, or the neutral, excuse me, now on carbon. It'd be neutral, and the plus would move over here. Notice I didn't say minus 1/2 and, or I mean, in this case, actually be plus 1/2 and plus 1/2, like I said you could do here. So this one, upper one, I'm going to specify it is easy to say plus 1/2, plus 1/2. Down here, you cannot say it because nitrogen and carbon can handle a charge at a different capacity. Plus charge on a carbon violates the octet rule. Plus charge on nitrogen, octet rule is still okay. So it actually will be maybe 80% of the time here in 20, or maybe 90% in 10. But I can no longer say half and half because it's no longer symmetric. Plus charge on a carbon and plus charge on nitrogen are not equal. So the compromise, we just put a delta plus. If you want to be specific, put a little bit bigger delta plus on nitrogen, smaller delta plus on carbon. Okay, so a lot has been thrown at you, these rules, and resonance is one of those things you can only gain it through practice. So guess what we're going to do multiple examples of? Example after example. I plan to do fewer examples in lecture than here, so hopefully you watch through all of these and you'll do a few extra than what we'll actually do. But I want to figure out what the arrows are. So notice that, as mentioned earlier, we went from 1 charge to now 3 charges, but the net charge is still the same. Negative, neutral, neutral, neutral. So overall -1. Negative, positive, negative. So overall negative. So we didn't change charges. All we can do in that case is figure out what got broken. So pi bond was here in the beginning. It's gone in the end. So I must have taken the pi bond and broken it. So pi bond became a lone pair. When it did that, notice the extra pair of electrons up here. There were 2 lone pairs, now there's 3. Notice the 3 bonds, or 4 bonds here, turning into 3 bonds. Loss of electrons leaves a positive formal charge. Gain of electrons forms a negative. Okay, in going from this structure to this structure, I went from 3 charges to only 1 charge, so I must have now formed a pi bond. So in this case, it just undoes what it did before. Lone pair becomes pi bond. Pi bond now is the 4th bond to carbon, so the plus charge is gone. I went from 3 lone pairs to 2. Negative charge is now gone. Positive charge is now gone because they cancel one another. You'll notice, though, my arrow starts from the pi bond, and it's roughly the middle. I didn't draw it perfectly, and it ends up on an atom. So if the arrow starts at the pi bond and finishes on an atom, then a pi bond became a lone pair on an atom. Notice I start at a lone pair and go to the middle, roughly middle of that bond. So when I go to the middle, that implies I'm making a bond. So it's very specific the way we do this. When you pay extra careful attention to detail early on, make sure you draw them right. So on early quizzes and early homeworks, like the first question or the ones early in our resonance experience, I'm going to be really anal about marking points off if they aren't perfect at first, just to get in the good habit. Later on, if you understand what you're doing, that's perfect. That's what matters. But getting in good habits early in the process helps. So overall, we had a pi bond here. We have a pi bond here that's formed. So I'm going to draw a dash line here. O's are equal. So if I wanted to, I could say -1/2, -1/2, because they're going to share it roughly equally. Okay, so this, and again, I want to try to use structures that are realistic. So acetate is actually really common in both OChem and bio. This structure here, an amine, going over 1 carbon and a carbonyl, has a peptide linkage between what used to be an acid and what used to be an amine, connected to an alpha carbon and a carboxylic acid. So it's an amino acid, but specifically, it is 1 amino acid bonded to a second one, so it's known as a dipeptide. So for those of you playing bio, this is 2 amino acids linked together. I haven't specified what groups are coming off of here, so it's really glycine and glycine if you want to know specifically amino acids. But again, I always want to point out our OChem pretty much exists, one, for us to build things. That's one cool thing. But the second reason is to support and explain a lot of bio concepts. So I'm going to try to do bio examples and point out along the way when I'm doing them. So I chose to do a dipeptide or diglycine. And in this case, when I look at what we now have a pi bond where we didn't, and we lost a pi bond. So I say to myself, pi bond becomes a lone pair becomes a pi bond. So I had a pi bond between carbon and O. It's gone now. So I'm going to say, let's make this go up here. Pi bond becomes a lone pair. Check. And then lone pair becomes a pi bond. I'm going to try to draw that arrow prettier. You're going to hear me complain about this program's penciling isn't that great. So hopefully you can still make out that that's an arrow and that's an arrow. Pi bond to lone pair to pi bond. Check and check. When I lose electrons, the residue is a positive charge. When I gain electrons, the residue is a negative charge. So when I move these electrons around, it became a charged species. Okay, so I'm going to draw a dashed line here and here, but I would not draw them with equal delta, or the delta minus and delta plus form isn't going to be as prevalent as the neutral species. We'll discover why and why. Okay, let's do this again. Let's try to figure out where the arrows go. So draw the arrows that correspond to the following resonance structure conversions. So let's see. This stayed the same. Oh, this is different. This pi bond is here and it's gone. This pi bond, there is no pi bond here. You have one here. Positive means I must have lost the electrons. Negative means I must have gained them. So once again, pi bonds become lone pairs. As we're seeing here, we had a pi bond here. It's a lone pair in this case. So pi bond becomes a lone pair. Again, I'm drawing it from the center of the bond to that carbon atom. On the lower side, I have a pi bond here and a plus charge, so this lone pair must be lost. So pi bond becomes a lone pair becomes a pi bond. I'm to decide not cut through the molecule to do it, but however you draw it is fine. But lone pair to pi bond, check. Pi bond to lone pair, check. For the second part of it, this part staying the same, this negative charge is gone. I now have a pi bond gone and negative charge up here. Lone pair is gone, so lone pair must be turning into a pi bond. And the pi bond must be turning into a lone pair. Perfect. So negative charge is gone and a pi bond is formed, so lone pair became a pi bond. Pi bond is gone, lone pair is formed, negative charge is now moved up here. Okay, I hinted at it last time. I want to emphasize this again. You would prefer to have uncharged species. When you have a charge, it's going to be attracted to things. When it attracts, it reacts. When it reacts, by definition, it's unstable. So this will be your predominant resonant structure, but these are viable all-octet resonant structures here and here, so they exist. So the hybrid I make, the composite of all of these, might be, let's say, 90% of this one, maybe 2% and 8% or something. And I'm just tossing numbers out there, but it's going to be mostly this, but it's just enough of this that I have a slight delta minus on that oxygen, and it can react as such. So when you get deeper into biochem, you're going to discover that when you form beta pleated sheets, alpha helices, when you start having hydrogen bonds in the backbone, it's actually the O that donates electron density because of this delta minus. It's typically an H on a nitrogen that, because of this plus charge, is the most susceptible to H bonding. And so it'll actually be the one that interacts. That's something for another day. If you're taking biochem and you're interested, you want to come back and ask, please do. So delta minus here, delta plus here, small delta minus, small delta plus. But delta minus means it's going to share electrons more, so it's the lone pair donor in a hydrogen bond. Delta plus here means it's going to make, if this is an H, make it slightly more acidic. It'll be the hydrogen bond receptor. Okay. Another example here. This one doesn't look like anything's changed. I don't see any charges. I don't see any lone pairs, but it's real subtle what's happened. The pi bonds have gone from vertical left and sloped horizontal on the right side to sloped horizontal on the left side and vertical right. So pi bond became pi bond became pi bond. It simply moved like this. This one moved here, caused a domino effect to move this one here, caused this one to move here. So you'll notice, again, I start with a bond and finish with a bond. So I start in the middle, finish in the middle. I don't go into atom, because if I go to an atom, that would be a lone pair. So pi bond becomes pi bond. Pi bond becomes pi bond, pi bond becomes pi bond. So if I wanted to redraw this, I could draw a dashed line here, 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 representing half the time it's pi bond, half the time it's not, half it is, half it's not. You're going to see in the textbook, and depending on like where else you study, you might see this structure coming in, where you have this benzene ring, as it's called, represented by these 6 carbons in the 6-membered ring, and then a circle that represents this resonance structure. This is shorthand. So this molecule is something known as toluene or methyl benzene. And benzene, you're going to hear, is highly stable because this resonance is known as an aromatic resonance. I'll get into it in another chapter, but it makes it highly stable. Okay, so now we're going to do things a little bit backwards. Not so much backwards as that, but we're still going to add arrows in, but now we're going to try to trace something all the way around, like we just did with benzene. So in every single case, we end up getting the same thing. So if I do it thoroughly once, I should be able to solve it later on. Lone pair is here. Now it's a pi bond. Pi bond is here. Lone pair goes over there. So this is a case of a lone pair becomes a pi bond. And again, let me be a little more anal, make sure it lands in the center. Pi bond becomes a lone pair, so I'm going to go to the atom. Didn't draw it well, so I draw it this way. Better, not perfect, but better. So this lone pair became a pi bond. This pi bond became a lone pair. So moving down, going to do the same thing. This lone pair. And now I'm going to cut across. Do that. And is that one also okay? So the big thing, can you make sense out of where it starts and where it finishes? Lone pair finishes in the middle. Pi bond finishes over here. So I'm getting a little bit more lazy about it. I'll do this one this way this time and this one this way. And I really don't care that much whether you do inside or outside as long as there's clarity in how you're moving things around. So in each case, there's a pi bond becomes a lone pair. So it's the same sort of thing, but this again is a case where that negative charge can move all the way around. So it's highly stable. It can be on, let's say, carbon 1, carbon 3, carbon 5, carbon 2, carbon 4. Could go back to carbon 1. So we move all the way around. It's resonance stabilized. So that makes this anion surprisingly stable for a carbon with a negative charge. Carbon doesn't like negative charge, but cyclopentadienyl anion, incredibly stable. I want to toss one more. This is going to get in the realm of biology. Biology has a lot of structures that have nitrogens in this sort of every other position. And it becomes really important to reactivity. And again, I don't want to spoil an entire class down the road, but knowing the resonance here will help a bunch. So again, let's look at what's changed from one structure to the next. Lone pair, gone with a plus charge. Sigma bond, now a pi bond. So this lone pair must be becoming a pi bond. So I'm going to say this one's going to go in here. And I'm going to redraw it to emphasize the middle more. So apologize for the bad arrow, but it landed in a better spot. That's 5 bonds of carbon, so something has to break. It has to be this pi bond. Lone pair becomes a pi bond becomes a lone pair. So start with the center, end at the nitrogen. Okay, so perfect. I have one. Now I want to compare this structure to this. This pi bond is gone, so this one is now going to break. So pi bond becomes a lone pair. That's exactly what we're seeing here. Plus charge goes away. My new pi bond is over here, so this lone pair must be the one coming in. And notice the repetitive nature of it all. Lone pair becomes a pi bond a lone pair. Lone pair, pi bond becomes a lone pair. We seem to do this over and over and over. Resonance arrows show that it's just moving electrons, not nuclei. But that really is the essence of resonance. Dashed lines represent sometimes a pi bond, sometimes not. Excuse me for a moment. Do apologize. So positive charge is resonating from the lower left nitrogen, the upper nitrogen to the lower right nitrogen, meaning a third of the time it's in each one. Because of just not perfect symmetry of this, it might be a little more often here than these two. So it might be minus like 0.31, minus 0.31, and minus 0.38 or something like that. We'll come up with ways to figure that out, but for now, just happy, not minus, but plus, excuse me, plus 0.31, plus 0.31, and plus 0.38. We'll come up with reasons for why it would be what it is eventually when we get into that space chapter next after this. But hopefully this is starting to fall into place and you're seeing the pattern. So this case, we have mixed it up. So I apologize that I was behind the slides when I made that statement. But now I want to figure out what was there to begin with. So we have the arrows. Now we got to figure out what used to be there. Okay, so fill in anything that's missing, bonds, lone pairs, whatever it may be. So here we have a pi bond become a lone pair. So I should get a lone pair from this arrow. Check. This pi bond is moving from one position to another. So I'm going to draw a pi bond here. Check. And this lone pair is coming in and becoming a pi bond. Check. I feel really good, except I also forgot, timeout, I don't want to do it in the same color. I want to pick a different color. Check. So I did the movement. Lone pair became a pi bond moved, pi bond became a lone pair. But what I completely forgot, and I need to pay attention, if electrons are moved in this direction, the wake of the electrons moving away is the absent electron, which is positive. And the result of these electrons moving over be a negative charge on the O. So checklist. Make sure pi bonds become lone pairs become pi bonds can move. Make sure I know what type of movement it is. So I'm going to inventory again. Pi bond becomes a lone pair becomes a pi bond moved from one spot to another. Okay, so I know the type, but also when electrons are lost, leaves a positive in its wake. When electrons are gained, creates a negative where it landed. So I have a new set of rules, or I just have an expanded set of rules. I'm going to see how I do. Again, I've started that same glycine, diglycine residue again. I want to emphasize that. Pi bond became a lone pair. Sorry, right here. Lone pair became a pi bond. So let me do that again. Pi bond becoming a lone pair. We'll put this up here. And now I want to pay attention. That's where electrons are finishing. So I want to put my negative up there. Lone pair became a pi bond. Check. Put my pi bond here. Ugly, I'll draw it again. Better. Positive charge. So I'm hopeful that as you go through these, you start seeing a pattern. We do the same thing over and over. And when you see that pattern, recognize that, it gets easier and easier and easier. So let me throw yet another one. And I'm hopeful that if I'm going too fast here, you can slow it down and repeat it. It is definitely in your best interest to sit and write all these down. You'll also bust me for being totally lazy, because am I doing the same examples over and over? You bet, and on purpose. It's not just laziness, but it's also to emphasize that you saw it from one aspect, now you're looking at another. So having done it once, hopefully that information sticks. Lone pair became a pi bond becomes a lone pair. So again, let's start with this one. It's going to become a lone pair. It's also going to get rid of the positive charge. It used to be a positive. So when you add electrons, it's going to add a negative one to the positive, and it's neutral. Over here, lone pair becomes a pi bond. So a positive, and it's got to carry a plus charge because you now lost electrons. Total plus charge here, +1 for the overall molecule, total plus charge of 1, and it's here on the nitrogen. And actually, let me be a little more specific and draw it on the nitrogen. Did not mean to switch to black. Okay, so sorry for the Wednesday lecture 3 popping up. That's going to be additional resonance. I'm going to stop it here. Thank you for playing along, and I will see you very, very shortly.